In this presentation, we will discuss how to do different pH calculations in buffers, including how to use BAA tables in the Henderson-Hasselbalch equation. Before we add anything to a buffer, we always have to calculate its pH. We know buffers consist of an acid and its conjugate base, and we have our Ka expression for this equilibrium. If we rearrange our Ka equation and take the negative log of both sides, what we get is that pH equals pKa plus the log of the base concentration divided by the acid concentration, which is known as the HH equation. Now let's practice. If we have 0.5 liters of a buffer that contains 0.4 molar acid and 0.3 molar of the conjugate base, and we know that the Ka for the acid is 1.00 times 10 to the minus 5, we need to find the pH of the solution. First, we want to find the pKa. pKa is the negative log of the Ka, so when we do this, we get 5.000. Now we use the HH equation. pH is equal to our pKa, 5.000, plus the log of the base concentration, which is 0.300 molar, divided by the acid concentration, 0.40 molar, and we get 4.875. Now we're going to calculate the pH of our buffer after we add strong acid. Strong acid reacts with the conjugate base component of the buffer. So we're going to figure out the pH of the buffer if the buffer contains 0.4 molar acid and 0.3 molar conjugate base, and we add 0.1 liters of 0.5 molar HCl to it. The first thing you always do is solve for moles. So for A minus we have 0.5 liters and 0.3 molar, so we have 0.15 moles. For HA we have 0.5 liters and 0.4 molar, so we have 0.2 moles. And for HCl we have 0.1 liters of it and it's 0.5 molar, so we have 0.05 moles. Now we make our BAA table. Remember, in our BAA table we always use moles, not molarity. So before the addition of HCl, we have 0.15 moles of A minus, 0.2 moles of HA, and 0.05 moles of the H3O+, and they haven't reacted with each other yet. Then, at the addition, the 0.05 moles of H3O+ reacts with the A minus, so we subtract that from the left and we add it to the right because HA is generated by the reaction of H3O+ and A minus. So after the addition we have 0.1 moles of A minus, virtually no H3O+, and 0.25 moles of HA. Now we can use our trusty HH equation to figure out the pH. And we know that in this equation, since the volumes are the same, we can just use our moles instead of molarity. So we have pH equals pKa plus the log of base concentration divided by acid concentration. And when we do this calculation, we get 4.602 for our pH, whereas before it was 4.875. So you see it changes, but not by much. Now we're going to calculate the alternative situation where we add strong base to the original buffer. So if we add strong base to the buffer, it reacts with the weak acid HA. So we want to know what the pH of a buffer is if we have 0.4 molar HA and 0.3 molar A minus if we add 0.1 liters of 0.5 molar base to it. So the first thing you do again is calculate the moles of each thing. So for acid HA we have 0.5 liters times 0.4 molar and we get 0.2 moles. For A minus we still have 0.5 liters and we still have 0.3 molar and 0.15 moles. For OH minus we have 0.1 liters and it's 0.15 molarity, so we have 0.05 moles. Now we use our BAA table again with moles, not molarity. So for HA we have 0.2 moles, for OH minus we have 0.05 moles that we're adding, and for A minus we have 0.15 moles, and we ignore water. Then when the reaction happens, the OH reacts with HA to remove 0.05 from the left side and generate 0.05 moles on the right side. So after the addition we have 0.15 moles of HA, no OH minus, and 0.2 moles of A minus. Now we use our HH equation, and we know that pK is 5, which we calculated earlier, and again we can use moles instead of molarity in the HH equation because our volumes are the same. So when we perform this calculation we get a pH of 5.125, and when we started we have 4.875. So again the pH changes towards the basic side, but not by much because we have a buffer solution.